So let's get started. We're recording, perfect. So last lecture we did a shear flow problem, closed section and open section combined, and then we switched to the torsion of closed sections, basically thin wall, and we stated we recalled our equations or our assumptions for torsion. We have no direct stresses, no shear stresses in XY plane. And with that, we looked at how the shear flow equation is affected if we have a thin wall and then with torsion. So we stated, like, if we recalled our equilibrium equations that we used to derive the shear flow equation, we noticed that we had a portion that was the variation of shear flow with S, dQds, or partial Q partial S, plus T multiplied by partial sigma z, direct stress in z, with respect to z is equal to 0. So if we take our assumptions into account, we don't have any direct stresses, so sigma z is equal to 0. Therefore, the partial variation with sigma z with z is also equal to 0. So then we have left over our the variation of q with respect to s is equal to 0 in the z direction, and the variation of q with respect to z in the s direction is equal to 0. So for this to be true, that means that q cannot be a function of s, so therefore q must be a constant value, or at least not a function of s. And with that, basically what that means is that if we have a torsion problem and pure torsion on its own, so no shear forces applying to it and other forces, then the shear flow in the section due to torsion must be a constant. And then we stated, like, okay, well, we know that torsion is an in-plane moment, so, and if we multiply the shear flow over a segment ds, we get a force, and if we multiply that with an arm with respect to an origin or an axis arm, we get a moment. So we could do that, and then we basically noticed that if we take the summation of all those forces multiplied by the arms, it must be equal to the torsion, and therefore we could state that torsion is equal to the circle integral, or circumference integral, boundary integral, I think that's the correct definition of it, of q multiplied by p ds. And then we also recall that p ds over the entire circumference of the cross section is nothing else than twice the enclosed area. So the torsion yields a constant shear flow and is basically scaled by 2 times the enclosed area. So the next step, where we left off, was okay, let's define the rate of twist, and I think the rate of twist is similar to what we did earlier. I have to go back a bit. So yeah, so we have our rate of twist. So this was for closed section, and now we can, so go back a bit, a couple of slides to the closed sections or solid bars. And we got our rate of twisters down below. So now we're going to do the same, but then for closed section, basically a thin walled structure. And for that, we're going to continue on the board. Switch. Perfect. So to define the rate of twist, you can do it a couple of different manners or different ways. So we still have our T is equal to G times Gj times d theta dz. And so yeah, you can do it a couple of ways. And the method that I'm going to use is basically an energy method. So we basically define the total work done, or total energy in our system, and we define that as equal to 1 over 2, so half times the integral over the volume of the shear stress over the shear modulus integrated with respect to the volume. So this will be our total energy. And again, the method that we're going to go through right now is just one of the ways that you can find the shear rate of twist for a thin wall structure on pure torsion. The derivations are useful to know, and they're, like I said, a couple of different ways. So, but you don't have to be able to reproduce. We are just going through the steps to see how we get to them. So here we know that shear stress is equal to the shear flow divided by thickness, so we can substitute that back in. Then we get integral volume. And we also know that in this case the torsion is equal to 2 times the enclosed area Q. And by the way, sometimes I forget the subscript E, but in this case it basically refers to the enclosed area. So let's do that. What we get is, so we can rewrite this as Q is equal to T over 2AE. We can substitute that back in. And what we get is let's do the volume still. Let's do an intermediate step first. Q squared TB over T squared G. And first what we do is, let's forget about this 1 minute. We go from a volume integral to a surface, because basically what we will have, we have a beam, we have our surface, the circumference, and this is just the length of the beam. So we know that the volume must be equal to the area times the length or the height. So we basically can transform this to a surface integral, and then what we get is Q squared L. So that's basically the length. So we so the volume dB is basically L times ds. So we get T squared G, and then we get ds here. And we also know we have now the total energy as a function of our shear flow. So let's say U as a function of Q. And we also know that the total energy must be equal to the total energy due to the torsion, say function of torsion. So the total energy as function of torsion. This is basically a standard formula for, in this case, for torsions. So we know, let's write that here. So total energy due to torsion is still U, and it's equal to 1/2 T times the total twist angle. So now basically what we can do is equate these two together in order to get a function for the rate of twist eventually. So let's delete this, move this up. So we set here, we transform this to a surface integral. And at the same time, we also know total energy due to a torsion is basically how much, if I have a torque to it, how much it's twisted, multiplied by half, you get the total energy for that. So now we can equate these two together, so we can get rid of the half. So we get half G. And now we use that T is equal to 2 times the enclosed area Q. So Q is T over 3AA. So we plot that back here. So get left hand side remains the same. The right hand side changes to T squared L ds. And then what we get here is 2 times 2 squared becomes 4. This becomes A squared. A squared T squared G. And we still have our integral bond ds. Now we can basically get rid of the half on each side. We can get rid of the 1t. And now we have basically our rate of twist or twist angle being equal to TL times TL over 4 A squared T squared over G. I forgot one thing. Let me see which step that was. When I went to the surface integral, I forgot to add a T here, by the way, because the thickness is important. So we actually have a T here. So 1T drops out here as well. So now we can look at this formula. We know a couple of things that are constant that don't vary with along the surface, and a couple of things that do vary with along the surface. So let's do that. So we know that theta, rate of the twist angle. So torsion remains constant because it's applied. The length of the beam does not change with the circumference. So that's constant. 4 times the area does not change with the circumference. So that's a constant. And then the things that can change with the surface are the thickness and the shear modulus. So now we have our twist angle due to torsion and applied in a thin-walled case, cross-section case. There's a function of a couple of constants, like the torsion applied, the length, and the area of the cross-section. And the things that can change are the thickness and the shear modulus. And these things you have to think about it like you can have a cross-section that's basically made out of 2 materials with certain different thicknesses. Say this is T1 and aluminum, and this is T2 and titanium. So you can have a fuselage that's made out of multiple thicknesses, so you have to take that into account. Therefore, this part must be within the integral bond in order to take that into account. And of course, we, in our solid sections, we said like, well, this is the twist angle, and if you want a rate of twist, that's basically the variation with respect to length. So if we do the theta dz, the rate of twist, basically what happens then, the L drops out, and your integral becomes this. And let's see what we had previously. So this is for closed section thin-walled, and if you recall correctly, for the closed section we had this. So if you change this, let's do it like this. So now the area becomes important and the thickness becomes important. Previously we just had the shear modulus and the torsional rigidity. So there's a difference between it. Okay. So with that said, we can do a quick small example. I'm gonna go to the lecture slides. There it is. So let's do this small example, and we recall that what we just have derived, we're going to apply that to this example, and we're going to see how certain things may affect our requirements. Say, let's this here. Theta dz is equal to the torsion over 4 times the enclosed area integral of ds gt. We also know that torsion is equal to 2 times the enclosed area times the shear flow. So we're going to apply this equation, these two equations that we just derived to this in-class problem. So a couple of things. It says a thin wall circular beam, diameter of 200 millimeters, 2 meters long, and it's constrained on both sides. So let's draw that. We have constraint on this side, constraint on that side. We have a concentrated torque in the middle, 30 kilonewton meter. We have maximum rate of twist. Oh no, maximum shear. So tau max is given as 200 Newton per millimeter, so 200 megapascal. And G is given as 25,000. Let's call this Newton millimeter squared. And the max rate of twist, so theta max is 2 degrees. So 2 degrees. So, okay. So a couple of things before we can actually start. We have to realize these equations are basically derived when we have a torsion beam basically clamped on one side, and we have a torsion applied on one and at the other end. So this is a beam basically clamped on two sections. So in order to basically apply this to that, we basically have to cut it in two and assume that the torsion is equal on both sides. So that's one of the tricks that you have to realize in this problem. You cannot just apply it straightforward. So what happens is basically we cut it in two. And we say on each side we have 15 kilonewton meter applied. So the length becomes 1 meter on each side as well. And now we can start with our problem. I think the problem is, the question is calculate the minimum thickness, so T min. And what we're going to figure out is that there are going to be two conditions that we have to consider. First of all, the maximum shear stress. Which thickness do we need for here? And which thickness do we need in order to satisfy the twist angle condition requirement? So for the maximum shear stress, that one's quite straightforward. We know that, we know we can use this equation. We know the torque is given. The enclosed area is nothing else than just pi r squared. And we can calculate the shear flow. We can rewrite this shear flow as Q is equal to tau times T. So we can substitute that back in here. And now we have one unknown and one equation, one unknown, so we can solve for T given the maximum shear stress. So let's do that. So let's call that requirement 1. And this is requirement 2. So for 1, we can just rewrite this. Torsion is equal to 2 times the enclosed area times the shear stress times thickness. So if you have the maximum shear stress, that is our minimum shear thickness. And now we can just plug this back in. And for that we get, so T is equal to torsion over 2 times the enclosed area, tau max. So we get is 15 10 to the power Newton meter going to millimeter. So 10 to the power 3 to go to Newton meter, and then another 10 to the power 3, so 10 to the power 6 to go to Newton millimeters, because one work with the millimeters. And then on this side we have pi. Radius is diameter is 200. So d was 200 millimeters. So radius is 100. So we get pi r squared 2 times pi r squared. And then let me see. Tau max, that's given us 200 Newton millimeter. And then we get 1.2 millimeters out of it. So we know very straightforward what the minimum thickness must be. So the second condition, let's check that as well. And that's the maximum angle. So in this case, we basically apply the rate of twist. We integrate that with respect to z, so we add an L back to it. So we have theta is equal to TL over 4 times the area, the integral of ds gt. And in this case, since we have one material and one thickness, T minimum is equal everywhere. So these two are basically constant as well, G and T, and ds is nothing else than the circumference of the beam. So let's do that. What we get is let me do this. D theta d z. Yeah. So let's fill in our things that we do know. So ds, what's that? That's basically, I said that's the circumference, or the integral 0 ds. That's nothing else than the circumference, so that's 2 pi r. So that's 200 pi. So what we get is T over 4 times area of 200 pi over gt. G is a constant, so let's bring that here. This is T, d theta dz. So let's continue on this side. So if we integrate with respect to dz, or with respect to z, we get theta is equal to T times 4 times enclosed area, G, and then 200 pi over T times Z, plus an integration bound C1. So now we look back at what's this integration bound. So we have to apply the boundary condition. So we apply the boundary condition in either one of the ends. Let's say that Z starts from this side. So if you do look at Z at Z equal to 0, there's no rotation because it's fixed. So therefore, at Z at Z is equal to 0, theta is equal to 0. So if we plug in Z is equal to 0, what we get is 0 is something times 0 plus C1. Therefore, C1 is equal to 0. And this something is basically just this what we have here. So we know that our integration constant is 0. So now we have theta as equal as T over 4 times the enclosed area, G 200 pi over T times Z. So again, now we can look at the where basically Z is maximum, or where theta is maximum. That's basically the furthest away what we can get. So Z is equal to 1. So for theta max, 2 degrees, Z must be equal to 1. So let's say theta max at Z is equal to 1 meter. or in this case, since we're working with millimeters, 1000 millimeters. Okay, now we can plug in our values. So we get 15 10 to the power 6 multiplied by 200 pi multiplied by 1000. And this is equal to 4 times the area. We said that was equal to 200 pi times 100 squared. Then we multiplied by 25,000, that's our shear modulus, and that's our theta. And we still have our thickness, 1 over thickness here. And this is theta. And theta was 2 degrees. So 2 degrees. This equation, however, is given in radians, so we have to convert this to radians. So we basically multiply by 2 pi divided over 100. So 180. Is that correct? No, pi. So we get multiplied by pi of 180. So we have 2 pi of 180.
Should it be pi or 180?
Huh?
Should it be pi over 180?
Yeah, but it's 2 degrees. So 2.
No, not the 2 pi over 180, just the pi by 180. So if like you're converting from, I guess, degrees to
radians. So it should be,
it's 2 pi by 360, so pi by 180.
yeah, that's what we have, right? Now we have 2 degrees. Okay. So now again, we have one equation unknown. We can solve for t. And if we do this correctly, we get 2.7 millimeters out of it. So the key point is we have 2 requirements, the same problem. So if we just look at the maximum stress, we can do with 1.2 millimeters. But if we now also have to satisfy our second requirement, then we suddenly have to basically double our thickness. So this becomes important with torsions, not necessarily often with torsion problem, the stresses are not necessarily the issue, but rate of twist and the twist angle will be. So you have to keep that in mind that for a given torsion problem, you have to double check, especially when you're given the question, what's the minimum or what's the maximum stress, or what's the maximum deflection. You have to check all the requirements given. Okay. Any question regarding this? So for stresses, things becomes much easier, especially since the fact that we assume or that we know that shear flow due to a stress problem becomes constant. So if we look back again to our torsion, so if you recall our torsion, our thick wall, we had our, that was, if I recall correctly, and we noticed that this would find as our torsional rigidity. So it's also good to have a formulation for torsion rigidity for both closed, thick wall, closed sections, and thin wall, solids and thin walls. And if we want this basically J for solids, we already know, and we also want to have a J for say thin wall closed sections. and eventually we also want to have a J for thin-walled open sections. Because the torsion rigidity will give us a pretty good idea, similar to our moment of inertia, of how effective a certain cross-section will be in handling, in this case, torsion. So when we drive the same thing, but then for a thin-walled section. So the first thing is, if you recall again to previous lectures, torsion. So we had a certain cross section, y and x, and we said that we have a torsion applied to it. And this is thickness, and this was element S. And if we looked at, if you recall our governing equations, we had the variation of our stress equation in x plus our variation of our stress equation in y is a certain constant. So now what we're going to do is, when we assume a thin wall, we're going to look back at this segment, but we now say, because it's thin wall, our thickness is significantly smaller than our any of the length that we are investigating in S direction. So with that said, we basically have an infinite direction in Y and a very finite and small, negligible value in S and T, sorry. So what that means is that the variation So if we look at any location along the thickness, dx, and we look at the variation with respect to the y direction, it basically doesn't change. So we can assume that our variation with respect to partial y is not changing. So what that implies is that our variation or our equation becomes this. Now we could rewrite this. Eventually we took this equation and we rewrote it to 2 times g d theta dz is equal to f. This is basically from our solid section. So what we do for a thin wall, we look at basically a solid and we just assume that it's extremely in the extreme condition of the solids that we have. So we have very long length z and very small thickness d. So now we can basically equate these two together. So we get d theta squared x squared. And we can just integrate it twice to obtain our equation and evaluate the boundaries. So our stress function now becomes, so integrate this twice, becomes d theta c x squared over 2 plus bx plus c, which are b and c are our integration constants. And then we look at the boundary conditions. We look at phi at x is plus or minus t, so basically at these two locations. We know basically at these locations, since it's extremely small and we will not have any variations and no basic stresses and the boundaries, so these two must be equal to 0. So what we can do is just plug it back in. We'll get plus t and minus t. So what we'll get is 2g t of 2g d theta dc. Let's plug in minus t first. Minus t over, sorry, this is t over 2 because we're looking at with respect to the x-axis being the center. 2 plus b minus t over 2 plus c, and we're looking at also on the plus side, so t over 2. equal to C. And both of them must be equal to 0. So if you do this, we can basically, we have two equations, two unknowns, so we can solve for it. So we know that if we solve this, B is equal to 0, C is equal to G times d theta dz of T over 2 squared. So now we plug in B is equal to 0 to our equation plus C. So what we get is that our phi equation, our stress equation, becomes minus G d theta dz. X. We can take this out of the brackets. So we get, let me see. Yeah. X squared minus and then this 2 drops. So this is our new function of our stresses, our stress function. And then next step, what we do is, in order to come up with the torsion rigidity, we know that our torsion must be equal to 2 times the integral of phi dx dt. And if we write this out and take the integral, what we get, I'll skip the integral part, it's not that important, or not that interesting. So what you, this is dy dt, sorry. So what you will get dx dy, sorry again. So what we should get is that we get g d theta dz, then st cubed over 3. Now we can compare this torsion rigidity with our previous torsion rigidity. So we have for closed section torsion, or solid section, we have this. And when we have a thin wall section, what we get is let's just rewrite this slightly a bit. Theta dz. So by comparing these two, then we can conclude that G for thin wall must be equal to S times T cubed over 3. So by comparison, what we have done is, in order to look at a thin wall section, we basically said, okay, let's look at our solid section. We basically squeeze one of the thicknesses to more or less 0, and we elongate the other thickness, or the other length. And in this case, what we did is we elongated the y distance and basically narrowed the x distance. Because of that, we said, well, okay, then we don't get any variation for fixed x along y. So we could drop one of our terms in our governing equation for torsion of solids. And we basically went to our governing equation and we did the previous steps what we did for solids as well. But now it would basically just be in a function of x. And if you have the reduced the x going to an infinite small location. And then we said, of course, the boundaries, our stresses must be equal to 0. So we did our integrations. We came up with an equation for it. We came up with a new equation for our stress function. Previously we knew that our torsion must be equal to our stress function integrated over the x dy. So we did that, and we came up with a new equation for our torsion, in this case, of a narrow strip. And we call that narrow strip basically a thin wall. And then we compare since we start basically with the same formulation, we compare our solid section, what we start with, which are new derived for thin walled, aka our narrow strip, aka thin walled section, and we realize that for those two to be equal, since we start with the same equations, J must be equal to S times 3 times S times T cubed over 3. So this is valid for long rectangular sections, aka thin walls. So we can do the same thing for what we can now do is basically plug in our stress function into our frontal, so we know what our shear stresses will be as well. So if we recall our shear stresses, tau yz is equal to minus d5 dx, and tau xz was equal to d5 dy. But we said there's no variation with y, so this one is basically, we ignore this. And then tau yz, we basically take this variation with x. What we get is 2 times g x d theta dz. And then what we get is, if we look at the maximum, so if we look at the maximum one, what we get is then the x direction must be equal to t over 2. So we get g t d theta dz. And if we look at the torsion, we get d theta dz. And we can basically combine these two in order to get the following, and also combine the j that we just derived. So we get that tau max must be equal to t times torsion times the thickness over j, or 3 times the torsion over s t squared. So there are two additional equations that we could derive from the same principle that we applied. So for the remainder, I'll go back to the lecture slides. So we did this. Now for torsion rigidity, like I said, to determine that, we look at the narrow rectangular strips. So basically assume this narrow rectangular strip represents a thin-walled structure. Variation of y was equal to 0, and we use that governing equation, reduce the governing equation just as a starting point. We integrate twice with respect to x. We get our integration constants b and c. We evaluate our function at the boundaries of x, so at minus t over 2 and plus t over 2. We know that basically stresses those boundaries must be equal to 0, since we have tau xy is equal to 0 in a pure torsion case. So therefore we can reduce or compute our function of phi, our stress function. And then we integrate it twice with dx dy, not dx dt, by the way. So this must be a y. And then we basically integrate it twice, and we get that. We compare it to our torsion equation for solid, and we conclude that the torsion rigidity must be equal to s times t cubed over 3. And then the next step, what we did is we just looked at the maximum stresses of tau xy and tau yz. Again, since we have no change in direction with y, so we have phi dc, phi dy, partial phi, partial y is equal to 0, or neglected, and partial phi, partial x minus that, or the multiplied by minus 1 is equal to 2 times gx d theta dz. So we get our tau max, and we get our maximum shear stress as a function of the torsion, the thickness, and our torsion rigidity. So the next thing what we want to do is compare torsion rigidity of a closed section with the previous section was about with that of an open section. And we can use the similar principle. We can assume that we have basically a closed section, but it's extremely narrow strip is being cut open. And then if we look at the rectangular section, from that open section is basically similar to what we did with a solid, and we looked also at the narrow strip of that. But now our coordinates basically are slightly different. Instead of going in x and y, we're going to go around the surface with respect to s. And we say that the outwards stress, so the tau and z, is our variation with our frontal or stress function with s, and that must be equal to 0. Similarly, we have our variation along s with respect to z, so that's the phi minus the partial phi over partial n. And we use the same analogy, but then we use a different coordinate system to account for, like in this case, circular cross section. And we can do the same steps. We get that tau s c max is equal to the thickness times the shear modulus d phi dc, which is equal to the torsion multiplied by thickness over the j, the torsion rigidity. So, and again, for open section, our j, because we use the same principle, is still valid. So we still have j is equal to s times t cubed over 3. And if we have multiple segments, we basically have to take that into account by calculating this, or summing up the segments, different segments to get the overall torsion rigidity. So assume if this figure was half or 1/3 made of aluminum, 1/3 of steel, and 1/3 of titanium, then you basically have to take into account, or it's different thicknesses, let me say it like that, you have to take into account the segments, the thickness of each segment, and the pad of each segment. So that's the reason we have this summation, or an integral format, 1/3, and then the integral of the total pad of t cubed ds. So now we can basically look at what happens is actually if you have a closed section and an open section. So for a solid circular section, we know that if it's closed, we get pi r to the power 4/2. So there's a solid section. And we have closed ring, but it's a thin wall section. What we get is we can take the outer diameter minus the inner diameter and still use multiply that pi/2. And for an open section, as we got previously, is 1/3 of the integral. So let's assume that the integral is 1/3 times 2 pi. So s is nothing else than 2 pi times 2 pi r, or pi, yeah, 2 pi r. So we plug that in. In this case, the r is defined as basically the midpoint of the outer and inner radius. And we plug that in. We can compare the two difference between the closed section and the open section. And we know that and we can continue basically just comparing the two. So we can drop an, we can take it to, we can drop it to, we can drop the pi's. And at the end of the day, if we compare our closed section with our open section, we can see that it's equal to 3 times the radius, or the midpoint radius of our open section over our thickness squared. So let's assume a couple of standard values. So if you have 1 meter diameter, 1.1 meter, so 10 centimeters, and we have a thickness of 3 millimeters, then the difference, or the ratio between the a closed section, an open section is 3,333. So what this means is, in torsion, just how the torsion rigidity is defined. If you have an open section, your structure is significantly less effective in torsion. So the idea behind this is, if you want to design something in torsion, you don't want to go for an open section. You want to go for a closed section because then you get the full capacity, or the torsional rigidity is significantly larger. And of course, you can apply this to the maximum stresses as well. And in either case, you can follow the procedure. You basically look at the ultimate stress. You look at where the location of maximum occurs, so basically at outer bonds. And you will see that a close cross section can take 100 times higher torsional loads before it fails, or almost 100. So again, like for torsion, the principle is you don't want to go for an open section. Okay, and if you have a combined section, like previously we discussed combined section of shear flow in open and closed. Similarly, the combined section of our shear torsion rigidity is the sum of our two different components. So the torsion rigidity from combined section is the torsion rigidity of the closed section plus the torsion rigidity of the open section. And we can do a small example again. So the question is again, find the maximum, find the angle of twist per unit length, given that you have applied a torsion rigidity or a torque of 10 kilonewton meter. And we also have to find the maximum stress in the section. So a couple of things are already given. The nose area is given, so you don't have to calculate this area yourself. And the length of the wall of 1 to 2, the outer length is also given. So this simplifies our calculation a bit, or at least determining what those segments are. So let's do that example very quickly. And we can see again what the effect is of the torsion or the torsion rigidity of the open and the closed section. So from our previous equations, we're gonna just look at G times J, basically the torsion rigidity. So for the closed section, we use our equation of 4 times the area times G over the integral of ds t. And for open section, we use G times summation of our basically C ds. So let's do the top one first. The enclosed area. That's so that's the nose cell area. So if you look at the nose cell, this is an enclosed area. This segment is not enclosed because it's not closed. Simple as that. So that enclosed area is 4 times the nose area. There's a square by the way there. So let me see. That's 20,000 multiplied by G. In this case, it's 25,000. Then the integral of ds dt is basically the integral along the outer circumference. So in that case, we know that this area is 900 outer wall. This is 600. This is 300. So in this case, since we already taken into account our enclosed area, so we basically take this pad and this pad into account. So we get 300 plus so we get DS, that will be 900 plus 300 plus 600. So, and we have also, if you look at the problem still on board, we have different thicknesses. We have to take that into account. So we get is 900 plus 300 over, sorry, so 900 of 1.5 plus, now we have 300 plus 600 over 2. That's basically our total ds over t. And if we did it correctly, what we get is 5,000 10 to the power of 7. And then we'll get this Newton millimeter squared. And if we do the same thing for this segment, for the open one, it's equal to G 1/3 yes 1/3 right. Yeah, that's correct. So what we get is 25,000 multiplied by I made a mistake on this side, by the way. This must be 900 plus 300. I'll get to this 1 second. So this is 25,000, and then multiply by over 3, especially, and then we get ds t to the power of 3. So we have 300 multiplied by 2 to the power of 3 plus 600 multiplied by 2 to the power of 3. And we get 6 10 to the power of 7. So I'll go to the slides to explain a bit what I did. Let's go to the slide. So we have to take a couple of things into account. So we basically separate this into two components. A closed section, basically varying from 1 to 2, including this upper, this vertical flange, and an open section, basically 1, 3, and 4, okay? So when we calculate our shear stresses, or torsion rigidity, we're gonna basically multiply by G just to take that into account. So we have on one side 4 times the enclosed area, so 4 times this enclosed area, which is given as 20,000 multiplied by G, and the SDT as the S over T of this closed section. So this is 900. This segment is 300. So 900 plus 300 of 1.5. So the second basically part of the cross section is this open section 1, 3, and 4. So if we take that different segments and we take the summation of it, we get 2,500 multiplied by, in this case, since we have the same thickness, we can sum it together as 300 plus 600, so 900 multiplied by 2 to the power of 3 over 3. So that's how we calculate it. So now we can basically compare the torsion rigidity. So if we want to actually use this, if we compare the two, it's almost a factor of 1,000 difference between the two. So if we actually calculate the shear flows, we can more or less ignore the torsion rigidity of the open section at all. So in the correct section, you would say this will be 5,006, but because it's so small, you can basically ignore it. you type in 5006, then you probably get what 251. So again, and if you calculate this for the closed section itself, you can also do the same thing for the open section. So the maximum shear stress in the closed section by itself is 167 newtons, and the maximum shear stress at the open section is basically 10 newton per millimeter squared. And if you look at it combined, then you basically add the total two together. They can more or less ignore it. So again, it becomes very important based on simple problems that you can see that when you have a torsional problem, you basically want to stay away from any open sections, because stiffness or the resistance to torsion of an open section is extremely low. And especially when you compare it to a closed section, you can more or less ignore it. So we can now take this same methods to a next one step further, and we can look at how, because we just compared a torsion open and closed, compare them to each other, we can see how that applies to, say, at the bending case. So in the bottom you see basically four figures: a C, an I, a different C, and a closed section. And if you look together, look closely, the dimensions are chosen in such a way that basically they have all the same neutral axis, and therefore, if you look at it, they will have the same moment of inertia based on how they are chosen. So if you look at the maximum stresses from a bending perspective, if you recall our stress equation, that will be sigma z is equal to the moment m, or applied moment m, multiplied by y distance from neutral axis over ixx. If your applied moment is the same, if your moment of inertia is the same, and based on dimensions, your maximum y will also be the same. So it doesn't matter if you have now a C section, I, or a different C, or a closed section, all the maximum stresses will be the same. So what we had in torsion, that we said we want to stay away as far away from an open section as possible, is not necessarily true for other problems like a bending case. So now if you now compare this to a torsional case, we can see that the first three basically will be considered an open section. Therefore, the torsional rigidity is calculated by 1/3 of the integral of t cubed ds. And the 4-1 can be considered a closed section. And therefore, when we have when we compare these two to each other, then suddenly our fourth section will yield much better results than our previous cross sections. So again, if you have a problem, we have to design a certain structure that must cope with a couple of different parameters. You have to check basically all the boxes and evaluate all the cases before you can come up with a correct solution. Because, like I said previous slide, is if you have given this as bending, it doesn't matter. But in this case, it does matter. So, as an engineer, you must be knowing. You must think ahead, like, okay, where are all my force applying to it, and how can I design the perfect structure that can handle all my requirements. And of course, if you if you can go also to the maximum shear stress for torsion, it's a bit of a so in the torsion case, you basically look at the variation of the stress. You will know that the maximum stress will occur at one of these cross sections, and I will not go into much to depth. It's basically where you can basically create a circle with a maximum radius to it. So in this case, let's ignore this slide. I don't think it's that important. But the point is finding maximum stresses for the bending case was relatively easy, but finding the maximum stresses in the torsion case, we would evaluate all these structures, it will become a slightly more difficult problem. But then again, based on the cross section, you would already know that you want to go for the closed sections anyways. So with this said, we completed now 3 topics, bending, shear, and torsion. So we have 2 more lectures next week. What we will do is just go through problems to basically get ourselves familiar with doing stress problems and torsion problems. I'll probably do 1.5 lectures approximately focusing on shear force problems, and then half lecture on torsion, because what we'll see is that torsion problems are often very straightforward once you know what you have to calculate. And then next weekend, y'all get your second midterm exam, and and there you are, basically 48 hours. I think I will upload it on Saturday 9 a.m. and will be due Monday 9 a.m. And the same principles apply. Send it per email. You have the 48 hours. You can use OpenBook, OpenIndian, and you will be great based on that. Are there any questions regarding torsion? Okay, cool. Then I'll see you next week where we just do problem solving.